Okay, good. This is part A of the Introduction to Robotics, San Diego State University. So we learned about that the real robot coordinate system and naming the frames on the links and the joints, and also too many things in the previous class, right? And so now let's go to the most important thing in the robotics, that we say the Nauwit Hartenberg parameters. This is very important, that we know in robotics, even when you are doing the research, we know as DH parameters. Let me show you guys. So if you go to my lab website, we have publications on the experimental and theoretical robotics. So for example, this paper on the Automatica published, so you can see here. See, this is my previous PhD student Mustafa Bagheri, me and my collaborator. So it's table 1 is Baxter that I have in the lab, then I with Hartenberg parameters, A, D, alpha, and theta. So you have to know, when you're sending a paper out, you have to know about the Hartenberg parameters, because eventually you're going to use this in too many things. Okay, so this is the fundamental of the robotics. Okay, so I want to make sure. Yeah. Okay. So now look at this. Two links. Okay, let me plot it for you. And now we have this. Bear with me because I have to be very careful on this. Okay. And now here we have the other link on the top of this link. Oh, this is not good. This is okay. So on this we have two lines also, and one of them comes here, another also comes here, and they are being connected like this, and this comes here. Okay, now you have two links of the robot. Okay, so now I have to plot two many things here. One of them is that this is link I, this is link I minus 1, that's right. And remember, when you are actuating the joint I, so the link I is being moved, that's right. So this is what? This is your joint I. Okay, this is your joint I. This is the joint I. When I actuate this, okay, this link moves. Okay, when I actuate this link moves. Okay, so if you want to actuate this link, you have to put another joint here. So joint what? Joint I minus 1. So again, when I'm actuating this joint by a DC motor, so this link moves, and when I actuate this joint, this link moves. Okay, understand? So, and obviously this is gonna be, see, joint I minus 1, joint I, this is gonna be, yes, joint I plus 1. So joint I can be a number 1, so it's gonna be joint 0, joint 1, joint 2, or I can be 2, joint 1, joint 2, joint 3. Okay, this is just I'm plotting in general format. Okay, then this is the joint axis. I am doing this. This is so here we go. This is axis ZI, and this is, I have to change my hand. This is axis ZI minus 1, that's right. And this is axis zi minus 2. Sorry, remember from the previous class, because if you look at it, you understand. Okay, so now I am connecting these two z's together, saying that this angle is 90 degree. Okay, here's 90 degree, and also saying that here is 90 degree. So because two links on the space, we have to visualize. So, and here gonna be xi. What I'm doing, I'm setting up the frames attached to the links or joints. So the right hand rule gonna be yi. Understand? The same here, I'm continuing because I have to teach you. Here gonna be again a line that is normal to both. Okay, like this and like this. So this is gonna be xi minus 1, xi minus 1. So based on the right hand rule, it's gonna be yi minus 1, yi minus 1. Okay, so and I'm saying this distance as ai, as you have seen the paper I showed to you. I'm saying this distance as di, so the second denoted Hunterberg DH parameter, and obviously this is ai, this is going to be ai minus 1. That's right. And so if I transfer this zi minus 1 here to and show it here by a dashed lines parallel to that, that's right. This is say zi minus 1. I transferred here, that's right. So this angle between them I'm showing as alpha I. Okay, alpha I. So now if I transfer this xi here, okay, parallel to that, this is your xi, I'm transferring here, okay, xi, this angle between them gonna be theta I. So now you have four parameters: ai, di, alpha I, and the theta I. I'm gonna define, okay. So these four parameters you have to develop for any robotic system. The name is denoted Hunterberg parameters or DH parameters. Okay. Eventually, I will let you know why we are developing this. Understand? So, in any robotic system, you have to find DH parameters. Okay. So now we have a few rules for finding those. Okay. So the rules. Okay. Rules in robotic. So first you need to determine frames or set up frames, means OI, XI, YI, and the ZI for each link. You have to do that. Okay. Now, how we do it? This is right like this. 1. We assign z-axis to be the axis of actuation actuation for joint ith. Let me show you. You see that this link I is being actuated by the joint I, okay? So the axis of this is along with the z I naught minus 1, that's right? So right hand rule, you know what I mean? Use your thumb finger parallel to z I minus 1. So when you rotate the other finger, it shows that is actuated on that direction. So z is, see here? So this z gonna rotate this link in this fashion. That's right, on the space. The same gonna be rotate on this direction. That's right. Understand? So the z's we assign on the axis of the actuation. Okay. So for example, if the actuator is this as DC motor, okay. So it's rotating. Its rotation is in this direction. Okay. A DC motor. So the z gonna be this right hand rule. Z. If you have this configuration, okay, so it's gonna rotate in this direction, okay. I'm sorry, gonna rotate in this direction. So this gonna be your z. Oh, I'm getting over. Okay, z in this direction. Or if you have actuator in this configuration on the space, okay, so its rotation gonna be in this direction is rotating. This gonna be z. So z is on the axis of the actuation. Or if you have prismatic joint that you have sliding on each other, so this gonna be z direction. Okay, in the direction of the actuation. Understand? So we set up z's as you can see here. This z, this z, this z, and this z on the axis of the actuation. Understand? Okay. So simply these are parallel to joint axes. Okay, joint axes. I'm talking about the revolution joint. Okay, these are parallel to joint axes. This to joint axis. So on the other hand, if I want to magnify this, I'm taking this out. So this is the actuator, exactly like this. See, this is the DC motor. So that's why this is z I minus 1. Understand? The actuator here is like that. Okay. So now, as I said, if joint is revolute, zi is the axis of revolution. Okay, as I explained here, z the axis of, because this is revolute joints, they are rotating, that's right, axis of rotation. If joint is prismatic, zi is the axis of translational motion, as I showed here. See here, in this direction, they are sliding in this direction, so this is gonna be z. Clear? Okay. So once we make base frame or coordinate frame, base frame, we begin iterative process in which we define frame I using previous frame what? Frame I minus 1, as we did in this figure. See? I minus 1, then we are setting up frame I. Oh, this is minus 2, guys. I minus 2, frame I minus 1, frame I. Okay? Understand? So this is I minus 2, I minus 1, and the I. Okay? This is a iterative process. Okay? So we're starting from the base frame, going to up. Okay? Now, having these, we have to know how to calculate the DH parameters. We're starting with alpha I. Okay, here, this is the alpha. As you see from this figure, this is the angle between the z-axes, but we have to know it. Okay. Alpha I simply is the angle between zi minus 1 to zi, this direction. Get here, z to zi, not the reverse, this direction. Okay, measured about, oops, measured about xi. See? So you have to look at this. So it says we are measuring angle between zi minus 1 to zi measured about x. Okay? Understand? So that's it. So second point, in this figure, zi and zi minus 1 are not coplanar. Okay, they are in the space. They are not they are not in the same plane. Okay, they are not coplanar. So in this case, there exists. So we, after understanding that the alpha I is an angle between the z's measured through about the xi axis, so there exists a unique line. I'm changing the to emphasize line. Normal line means normal to both zi and zi minus 1. This line, look at here, guys. This is zi and this is zi minus 1. They are in the space, they are not the coplanar. There is a line, this line, that is normal to this and normal to this on the space. Okay, normal to this and normal to this. Again, look at here. This line is normal to zi and zi minus 1 on the space. Normal to this, here is 90 degree, and here is also 90 degree. Understand? and so this line is normal to that. Now change to blue, such that okay, this line connects both axes, zi and zi minus 1, as it does. Look at the figure, and it has minimum okay, length okay. This line defines, I'm changing the color, defines direction of axis xi and origin OI. So in this page we said how we define the z-axis for the frame I. Here now, using that line that is normal to both zi and zi minus 1 and has a minimal length on the space, after plotting that line, this line, okay, so this line, so this gonna gives you the direction of xi. So here gonna be your OI, obviously. That's right. So again, so I'm summarizing again. Z-axes are on the direction of actuation. Okay, if these are revolutes like this one, so these are very simple. Okay. Now if you want to find the xi to make a frame for this joint I plus 1, you have to connect z-axis to zi minus 1 axis on the space with a line that is normal to both axes, okay, and has minimum line. After plotting that, it's gonna intersect the zi, that's right? So this direction is xi, and you have the OI. So now it's gonna be very easy, that's right? How to define yi? Use right hand rule for yi. Okay, so until this point, look at here. So right hand rule says if you rotate by your 4 fingers from xi to yi, the thumb shows the zi. If you rotate from yi to zi, your thumb shows xi. If you rotate from by 4 fingers from zi to xi, shows y. So you can see that here is 90, so this is yi. So until this point, we could establish many parameters. First of all, we said if you have the revolute joints, the axis z's, zi minus 1 and zi minus 2, they are in the direction of the actuation. After that, we could you can connect this line on the space that is normal to both of the zi and zi minus 1. That gives you xi and the origin. That's right. Then right hand rule, you can establish yi. After having xi, you can measure the angle between zi minus 1 to zi by angle alpha I. So now you have 2 parameters, alpha I bingo and the AI bingo. Understand? 2 parameters of the DH. I'm gonna give you examples to clarify and practice. Okay. So so this is AI. So let me write the AI definition. So AI, okay, we had the alpha I here. We had the alpha I here. AI is DH is as DH parameter, as you saw in the picture, is distance along xi from origin of OI to the intersection of the xi and zi minus 1. I just one axis. Okay, so as you will see eventually for regular robots, AI gonna be like at the backstream lab, gonna be length of link. I'm gonna show you. This is a very simple version of what is AI. Again, it says distance along xi, obviously this is xi, along this from origin OI, yes, obviously, look at here. Oh. From origin OI, obviously, to intersection of xi to z minus 1. So this is AI. So this length is AI. Understand? So this is very specific definitions. It's not valid for everywhere. I'm just talking very specific wise. I will give you the examples. Okay. So and you know what, to avoid confusion, forget about this, because I want to make it simple, but this is not valid everywhere, so that's why forget about this now. Okay, so after having those, now let us see the third Dynamite-Hunterberg TH parameter, theta I, is the angle between axis xi minus 1 to x, again this direction, not reverse, measured about zi minus 1, as I showed here. Look at here. So after setting up all the coordinates, now look at this coordinate: zi minus 1, xi minus 1, yi minus 1. So if I transferred xi and put it here, so the angle, let me delete this because I wanna. So the angle measured from xi minus 1 to the xi, but you have to use right hand rule around the zi minus 1, that's right, thumb. Your thumb is on the zi minus 1, so the angle between them. So this is theta I. This is the fourth. What? This is the fourth Dynamite-Hunterberg. Here we go. Sorry, third. Okay. So this, now let us do the fourth, di. Okay. Di distance along axis zi minus 1 from origin OI minus 1 to the intersection of xi and zi minus 1. Okay, distance from origin of OI minus 1 to intersection of XI and ZI minus 1. Right? Okay. So guys, look at here. Let me delete this because it's too much. I'm making noise here. Also this. Okay, now we can see it clearly. So the distance along this axis, okay, from OI minus 1, here is intersect that we define OI minus 1, okay, to the intersection of XI, intersection of XI and ZI minus 1. Understand? Yes. So that is DI. Okay. Oh, this line is, this line, I did it wrong. This distance. Okay. So it is offset between the origins. Okay. It's offset between in the origins in the direction of ZI minus 1. Okay. This is the origin of this in the along with the XI, and this is origin of this. That's right. Understand? So this is your DI. This total is DI. So now we have it. Understand? So now let me do from simple examples to a little complex. Now is recording, or I'm just talking on the air. So this is the simplest robot that you can have. Here we go. A 2 degree of freedom planar robot. Okay. So, and this is your fixed frame. Obviously is O naught, X naught, and the Y naught. And you have this robot. Now you understand the dynamic counterweight parameters. This is one link planar. This is another link planar. Here you go. 2 link. This is too much. So 2 link. This. So the angle between here and here is θ1, and the here and here, this link has θ2. So here is A1, the links of this. Here is A2. Okay. Understand? So as I said previously, ZIs, they are in the direction of what? In the direction of actuation. That's right. So Z out is out here, that's right, coming out of the page. So here is Z naught, obviously. That's right. So because if your thumb shows the direction out of the page, this is the actuator, gives you such angle, θ1. Here the same is valid for this. This is out of the page, gonna be Z1. That's right. Suppose here is what we have these things. Okay, and here is you have Z2. That's right, for the end effector. They are out of the page. Okay. So see that now assume lines out of the page, normal to the page, Z0 and Z1. So the minimum distance that connecting Z1 and Z0 out of the page has minimum lengths normal to each other is this line. Is this line, guys. That's right. Is this line. That's right. So this is length of the link. That's right, length of the link. So here gonna be in this direction, gonna be x1, obviously. This is how we define the DH parameter. That's right. So now, based on the right-hand rule, here you're gonna say, this is very bad plotting. Let me plot it correctly. This. Okay. Here gonna be x1. That's right. Now, using the right-hand rule, gonna be here. Gonna be Here gonna be y1. That's right. So z1 is out of the page, x1 is in the direction of that a line connecting z0 to z1. That's right, with the minimum page. So this is x1 and y1. Clear? The same valid for here. Look at here, guys. The z1 is out of the page, z2 is out of the page. That's right. So the line that has minimum length connecting z1 to z2 is this line. That is normal to both of them. That's right. Is length of the link. So here gonna be x2. z2 is out of the page. Using the right hand rule, gonna be y2. Simply like that, you are now set it up the coordinate frames. You set up the coordinate frames. So this line length is what? You have to make a table. Like as I showed in the paper that we published, and we are publishing in robotic field, you have to make a table. You have 4 parameters. You have to say link. Okay, link. How many links you have? 1, 2. 1, 2 link. Link number 1, link number 2. Okay, you have to do exactly like this. Well, for the exam, or when you are working as an engineer for a company, or when you are doing research, when you are a professor, whatever it is, okay? And say AI, alpha I, DI, and theta I. So we found that AI, that is a line that connecting Z0 and Z1 out of the page, has minimum length, is this line, A1. So the result is, for link 1 is A1. For link 2 we found is A2. That's right, the length of the link. So that's why I wrote in the previous pages that is length of the link. So for some specific planar robotic system, it is valid. Okay. So alpha I based on the definition is the angle between zi-1 to z. Okay, we are not blind. z0 is out of the page, normal to page. z1 is out of the page, normal to the page. z2 is out of the page, normal to page. So what is the angle between them? 3 parallel lines, zeros. 0 and 0. Okay, the angle between z0 and z1 to z1 is 0. z1 to z0 is 0 because they are the parallel lines out of the page. Understand? Okay. So let me go to theta I. Okay, theta I, we said, look at here. Theta I, the angle between xi-1 to xi measured about zi-1. Okay, guys, look at here. This xi-1 here is x0. Angle between this x0 and to the x1 measured about what? Measured about z0. Measured about the previous one. Look at here. You have to follow xi-1 to x1 from small to high, around the smallest one. So if you put the right hand rule, z0 gonna be angle between this axis and this axis gonna be how much? Theta 1. So it's gonna be theta 1. But I'm putting a star on top of that. Why? Because when the robot moves, this changes. This star means this angle is changing. Means angle is changing. Angle is changing. Now, angle between x1 and x2 measured respect to z1 gonna be how much? Yes, theta 2. Theta 2 star means it's changing. That's right. So now, what is di? Di is, based on definition, distance along zi-1 from origin of the previous to the intersection of xi. Okay, look at here. Along the z0, distance between the origin of this means this point, O naught, along this out of page, to intersection of xi and zi minus 1. Xi intersection gonna be here. Do we have any offset between them? Do we have? No. So it is 0. That's right. The origin of this O1 and O2, do we have any offset between them? No, it is 0. The same. The same. O2. That's right. Do we have any offset between the origin of this and origin of this? No. Gonna be 0. Okay? Because when you connect the x2 intersection to O1, intersection between this, and measured in the y-axis, gonna be 0. Sorry, what is the z-axis? Okay. Understand? So now you have this parameter. Now if I say find transformation matrix T2 respect to n the factor, I'm saying here I'm saying n the factor, like as the backstory I have effect in the lab, n the factor. If I want to see the end of transformation matrix I taught in part 7 with respect to the body of the robot or the base frame, it's gonna be, as I said, A1 respect to 0, A2 respect to 1. So this is homogeneous matrices, that's right. Here we go. 0, 0, 0, 1. First, O1 with respect to O0 has offset. What is the offset? A1. That's right. But you have to know this time with respect to which coordinate system we are talking about, with respect to O0, X0, and Y0. That's right. With respect to previous coordinate system. So here gonna be what? Here gonna be this coordinate system. Gonna be A1 cosine theta 1. This component, and A1 sine theta 1, A1 sine theta 1. These, no difference. So now the axes with respect to each other. So axis x1 gonna be what? Cosine theta 1. x1 with respect to y0 gonna be sine theta 1 and theta 1 and 0 obviously. Y1 with respect to x0 gonna be minus sine theta 1 cosine theta 1. I am pretty sure that you know, and because they are the parallel, these gonna be like that. Now for the A2 respect to 1, frame 2 respect to 1. Frame 2 respect to 1, again, the origin of the O2 respect to the O1 has these offsets, this. That's right. So we're gonna be A2 cosine theta 2, A2 sine theta 2. That's right. That trigonometry, and 0, 0, 0, 0, 1. And now the axis like the previous case, gonna be cosine theta 2, sine theta 2, and 0 minus sine theta 2. I'm skipping this because now I know, because I taught you several times, and because these are parallel. So with respect to and the result gonna be this cosine 1 2, bear with me, sine 1 2.
I can learn to understand you much better if I can get familiar with the way you talk.
What? 0 0 minus sine theta 2 cosine theta 2 and 0 0 0 0 1 0. A1 cosine 1 plus A2 cosine 1 2, A1 sine 1 plus A2 sine 1 2, 0 and 1. So here when I say cosine 1 2 means cosine of theta 1 plus theta 2. When I say sine 1 2, I say sine of theta 1 plus theta 2. Again, I want to double emphasize, triple time emphasize. In the homogeneous transformation, this is the distance or offsets between the origins of the frames. These are the origins of the frames, origins. But in the rotational part, this is the rotation metrics of axes. Understand? So now you have to deal with Hartenberg parameter. Okay. So I'm gonna have another example by the next week.